Hi, my name is Lazaro Alvarez, and today I will be presenting a paper titled Defending Against Malicious USB Firmware with GoodUSB. This presentation is for the CS6263 Introduction to Cyber-Physical System Security for the spring of 2019. The authors of this paper are Adam Bates, Dave Jing Tian, and Kevin Butler, all from the University of Florida. This paper was presented in the 2015 Annual Computer Security Applications Conference in Los Angeles, California. This paper can be seen with the provided link. To start off, USB attacks are becoming more sophisticated. Attackers nowadays are targeting the USB stack and embedding malicious code in the device's firmware to be able to secretly request additional USB interfaces without the user's knowledge. This is known as a bad USB attack, where the USB is capable of acting as a keyboard or be able to inject malicious scripts into the host machine. And the root of the problem of these attacks is that the USB stack has no restriction to what it can request. However, we can all agree that the most reliable source of information about a device's capability comes from the end user's expectation, correct? And with this idea in mind, it leads the authors to implement GoodUSB framework. As we may know, the USB interface is a dangerous vector for attack. In many organizations, use of USB flash drives are prohibited due to the potential of spreading malicious software within the organization's network. In response to this, antivirus softwares have become increasingly adept at scanning the USB storage for malware. However, as I mentioned in the previous slide, attackers are embedding malicious code in the device's firmware, and the host machines cannot scan USB firmwares, and antivirus softwares in the host machines are not positioned to detect or defend against such attacks. The root cause of this problem is the lack of access control within the enumeration phase for the USB protocol. For those who do not know, the enumeration phase is the process of exchanging information between the device and the host machine that includes learning about the device. The devices are free to request as many device drivers to be loaded during this phase, and we have no way of identifying what type of device it is due to the fact that during the enumeration phase, a malicious firmware can make any claims about its identity. To add more to the problem, standard USBs are too simplistic to reliably authenticate, and secure devices with signed firmware that could permit authentication are rare, which leaves us unclear on how to defend ourselves against these attacks. Who is the most reliable source of information about a device's identity? The user who plugs the USB device into his host machine. For example, a user can plug in a flash drive and they are aware that they did not plug in a keyboard. Therefore, using this key insight, the authors were able to design and implement GoodUSB, a host-side defense for operating systems against bad USB attacks. GoodUSB has 4 features: a graphical interface that prompts users to describe the device's identity, a kernel enforcement mechanism that denies access to features that fall outside of the selected device's description, a security image system to simplify device administration using security pictures, and finally, a novel USB honeypot mechanism to profile bad USB attacks and to log all communication that the USB attempts in a virtual environment. So let me cover a little background of USBs. The communication between a host and a device is done across a serial bus. Hence, the name Universal Serial Bus, aka USB, came to be. A simplified example of device enumeration for a USB flash drive is shown in Figure 1. As you can see, a series of queries are done to discover the information about the device's functionality. But this process we notice at the end, the device queries for kernel drivers to allow the device to function, and that can result into a single device requesting one too many interfaces from the host. Which is why bad USB attacks are so easy to accomplish, and the best part of it all is that the device can install all these interfaces without the user's knowledge or consent. This is why flash drives are very dangerous in organizations, due to the fact that they can be used in social engineering attacks where the compromise of a host machine can be as simple as tricking the employee to plug in a USB key. As a result, they prohibit or even ban the use of USB and even go as far as gluing USB ports shut to avoid employees from even using them. So during the design phase, the goal was to provide defense against bad USB attacks in a security-conscious enterprise environment. Traditional attacks were not considered. The design also considered an advanced persistent threat attack, which is the attempt of distributing USB devices with malicious firmware via supply chain compromise or social engineering. The, the design also considered that the device in use can make any claim to its identity during the enumeration phase by lying about its manufacturer and product ID. Finally, the authors also assumed that the state of the host system is in a correct state. The main problem in bad USB attacks is that any USB can request as many drivers as it wants. In response, the authors proposed the introduction of a permission validation mechanism that authorizes devices' access requests to individual USB interfaces. This proposed mediator is shown at a high level in Figure 2 that contains three components: a policy engine, a device identifier, and the policy itself. I will explain more of each component's purpose further on in the presentation. In the process of identifying USB devices, the fundamental requirement of any access control system is authenticating the subject. However, the problem is that we cannot trust any message that we receive from the device during the enumeration phase due to the fact that an attacker probably has rewritten the device's firmware so it can change its response during any message in the enumeration. Like per se, it can lie about its product ID. So instead, the authors came to a conclusion to use the user to describe the device's functionality during this phase. So the user will be asked, what do they expect the device to do, having them as a verifier for the claims that the device makes during the enumeration phase. This verification concept can easily be viewed in Figure 3. And so when the user finishes describing what the device's functionality is expected to be, the settings are stored in a policy database. And so, during this identification phase, three scenarios can happen. 1. The device's claim is consistent with the prior connection. 2. The device makes a different claim that matches an entry in the device database. And 3. The device makes a different claim that does not match an entry in the device database. Scenario 1 and 2, the user will be presented with an entry from the database and asked whether the information is correct. But in scenario 1, the user is most likely going to confirm that the information is correct. However, in case 2, the user notices that the information is incorrect and the device can be flagged as malicious. And finally, in case 3, the user is presented with the initial device registration dialog again, but since the user knows that the device has already been registered, they can simply report the anomaly and the device will be flagged as potentially malicious. So the device has been flagged as potentially malicious. What do we do now? Well, unfortunately, it's not possible to block the device from further interaction with the system. And the device cannot be blacklisted because every other time the device connects to the host, it can simply change its identity. Thus, the only option is to redirect the device to a virtualized honeypot. This allows the device to be observed while protecting the host machine. So what is a honeypot? Well, a honeypot is a computer or computer system that is intended to mimic likely targets of cyber attacks. It is usually used to detect attacks or deflect them. The main goal of the honeypots is to gain information about how cybercriminals operate. However, in the case of GoodUSB, it will simply be used as a virtual environment to observe the following types of informations, which are the device's information, the drivers that the devices request, and finally, all communications at the USB layer, which includes all keystrokes and IP packets sent or received over the network. So this all leads to the actual implementation of GoodUSB. First off, GoodUSB is implemented for Ubuntu 14.04 LTS, kernel version 3.13.11. In Figure 4, you can see the full architecture of GoodUSB, and this image introduces the four components that are highlighted in yellow. The first component is the user space daemon, which handles the graphical interface and policy management and also includes the logic for the USB mediator. The second is the KVM honeypot, profiles potentially malicious USB device. In the kernel space, the third component is the device class identifier as well as the limited USB HID driver that secures human interface devices by restraining them to particular kinds of keystrokes. So let's start off with the first component, the user space daemon. Most of the GoodUSB's functions are handled by a user space daemon, and it will include three subsystems, which are the policy engine, the graphical interface, and the device database. The netlink socket created in the kernel hub, which all of you might know is a Linux kernel interface used for the inter-process communications between both the kernel and the user space process. This is used to allow the interaction of the user space daemon with the rest of the USB stack to be able to perform USB device detection, enumeration, and driver matching or loading. The first subsystem under the user space daemon is the policy engine, which is responsible for determining whether the requested interfaces of a newly connected USB matches the user's expectations, and obviously enforcing the user's expectations if the same device is connected again. It also notifies the kernel to block the loading of particular interfaces or to redirect the device to a honeypot. The policy engine also maintains a mapping between lower-level interface types and a high-level summary of common USB devices. Examples of these mappings can be seen in Figure 5. The policy engine can operate in two modes, Basic and Advanced. In Basic mode, the graphical interface features high-level device summaries, and the user selects a single option that maps to the low-level interfaces. This can easily be seen in Figure 6, where the user is selecting a USB headset, and if you remember the mapping in Figure 5, USB headsets map to lower-level interfaces such as USB class audio and HID with limited capabilities. In Advanced mode, the graphical interface instead shows the lower-level interfaces and allows the user to make multiple selections. With this mode, the user has finer control over device functionalities and also supports devices that require uncommon interface sets. The next subsystem is the graphical interface. In Figure 7, it contains examples of all the different graphical interfaces. In Figure 7a, as we saw in the previous slide, that is the registration screen. This is prompted when the GoodUSB does not recognize the device. The next dialog box is Figure 7b, where this is the recognize device notification. Here, if GoodUSB recognizes the device, then the user can verify the device through either reading the descriptive text or checking that the percentage security image is correctly associated with the device. If any of the information is wrong, then the device can be flagged as potentially malicious and it will be redirected to the USB honeypot. The last dialog box in this picture is Figure 7c, which is a security picture screen. This is prompted to the user immediately after the device registration screen. The user is asked to select a security image to associate with the device. The last subsystem is the device database. Once the user space daemon has obtained the user's expectations and security picture is selected, this information will be recorded. The database is implemented as binary file and is synchronized with kernel space whenever a new USB device is plugged in. Ultimately, users have the ability to clear the database in the user space daemon, which provides a clean base in the kernel space once the machine is restarted. So, GoodUSB's honeypot is essentially a virtual machine mechanism used to observe the activities of potentially malicious devices. It is constructed to solely observe bad USB attacks as opposed to traditional honeypots because the traditional honeypots that I explained earlier when covering what a honeypot is are not capable of observing bad USB attacks because those systems emulate a device as opposed to a host and attempts to catch the host-based malware as it infects the device. So it was necessary to design a new USB honeypot framework. So the GoodUSB is a virtualized Linux machine containing multiple device profiling services. It supports two modes of device profiling. The simplest mode, the user space daemon, automatically redirects devices to HoneyUSB after the user flags them as potentially malicious. The second mode, the HoneyUSB, reserves an entire USB controller device on the host and is hoisted directly into a kernel virtual machine using pass-through technology. This helps because the infected device never operates directly within the host OS and is separated from the physical host machine. Also, the HoneyUSB contains an instrumented version of the GIO virtual file system because this helps to collect file level data which results to a detailed description of the read and write operations that are performed by the device. The third component that makes up the GoodUSB framework is the device class identifier. This is a kernel space component that summarizes the claims made by the device during enumeration. This contains all the device's information, including all requested interfaces. The SHA-1 digest is used as a device identifier in both the user space name and device database and the kernel device database. And for those who do not know, a SHA-1 is a cryptographic hash function which takes an input and produces a 20-byte hash value. If everything matches with the user's expectations, the response will be received and the kernel creates an entry for the newly device in the database, and the permitted drivers are then loaded. Regardless, the drivers will not be loaded until after the user approves the device. If the user does not approve, the user space daemon will redirect the device into the USB honeypot. The last component is the limited human interface device driver. The whole GoodUSB architecture is designed primarily to enforce least privilege on USB devices. Unfortunately, once the device has been approved for a particular interface, it has full capabilities which goes against this principle. And the devices that request HID interfaces allows a bad USB device to take nearly any action on the system. For example, a USB headset can request an HID interface to be able to control the volume of the internal speaker. But during a bad USB attack, the malicious device can take advantage of this. Therefore, GoodUSB has in place a copy of the linked USB HID driver and restricts the numbers of characters that can be injected by a USB device. With this limited USB HID driver approach, it can dramatically reduce the scope of bad USB attacks without needing to touch any specific drivers. So we have covered what actions took place into designing such a framework, and we were able to dive deep into the framework of GoodUSB and learn a little bit of each component that was implemented to create the framework. But now we can talk about how the authors evaluated this architecture. How did it perform against a variety of malicious devices? One of the first attacks they used was an HID-based attack using the rubber ducky penetration testing device. The ducky provides a user-friendly scripting language enabling different HID-based attacks. They load a basic Ubuntu terminal command script into the ducky, which opens an external window, and then performs several commands including checking password files. So once the author plugged the ducky into the host machine, the GoodUSB pops up, the device registration screen. Since the ducky appears to be a USB thumb drive, they choose USB storage and register it with a security image. But this attack fails because GoodUSB does not allow USB HID interfaces for USB storage devices. However, the ducky continues to function in its capacity as a storage device. Next, they use a Teensy USB development board to demonstrate more robust interface attacks. The Teensy is able to simulate not only as a USB HID device, but also as a USB serial device, and it can even act as a keyboard. The Teensy device can even go as far as act as a composite device, which is similar to how smartphones present themselves to hosts. So firstly, the Teensy is used as a USB storage form factor, but is acting as a serial device to transmit messages. But the attack fails because the user registers the Teensy as a USB storage device, and this results into the serial interface not being loaded, and none of the commands can be received. Then the authors configure the Teensy to act as a composite device to demonstrate how a GoodUSB will handle such device. This attack also fails because GoodUSB informs the user all interfaces that the device tried to request, and the user has the ability to whitelist individual interfaces. The next attack they used was a smartphone-based USB attack. They use an Android phone, the Nexus S, that contains a shell script called Bad Android that emulates a DNS-based man-in-the-middle attack. This attack requires USB tethering, which allows a USB device to present itself as an Ethernet card to the host. So the Nexus S is connected to the GoodUSB and it registers as a USB cell phone. The GoodUSB only allows the smartphone to use as mass storage and vendor-specific interfaces. However, once the author enabled the USB tethering on the phone, GoodUSB detected the new interface request and popped up a registration window asking for the permission for this new interface. If the standard USB cell phone without tethering is selected by them, then the potential man-in-the-middle attack is avoided. As you guys can see, GoodUSB handles itself very well against bad USB attacks, but how does it perform? Well, the authors use a Lenovo ThinkCentral desktop with a 3 GHz Intel Core processor and a 4 GB RAM. And they use a USB Logitech ClearChat USB headset containing 4 interfaces to test GoodUSB's performance overhead. As you can see in the table, the normal enumeration times are recorded there. As you move down to the GoodUSB steps, you can see the device identification This shows the overhead of the device class identifiers. The average overhead ends up being 9 microseconds, which the authors deem it to be negligible. The second row is the first enumeration. This is when the device is plugged in for the first time, where the user has to select the description that best suits the device and the security image, and this only introduced a 5.2% overhead. The second enumeration shows when the device has been recognized by GoodUSB, and this presents a 5% overhead. And finally, the honeypot redirect case where the device is flagged potentially malicious by GoodUSB, and as long as the honey USB is already started and running, the whole redirection needs only 262 milliseconds to allow the device to re-enumerate. Overall, the overhead is negligible during the USB device enumeration phase. GoodUSB is only the first steps to protecting ourselves from bad USB attacks. In their future work, they want to analyze further in depth the overall issue of allowing drivers to support as many devices as possible, which is ultimately violates the least privilege principle because it is providing a device with more abilities than it actually needs. And the authors are hoping to add more features to the GoodUSB architecture, such as profiling phase. Funny USB will inform the available device to interface mappings in the user space daemon graphic interface. And they want to use the Honey USB profiles to improve GoodUSB ability to predict the purpose of vendor-specific interface requests. So then the graphical interface can display the actual expected drivers that should be loaded to the user. So here we are. We have reached the end of the presentation. I would like to go over what we have discussed. Firstly, as I have mentioned over and over again, USB attacks are becoming more sophisticated. Our host machines and antivirus software cannot fully protect us from attacks. As bad as it sounds, we have no practical defensive solution against bad USB attacks. This problem all stems from the fact that we have unconstrained privileges in USB devices as it was shown in this presentation. And GoodUSB is a good start in getting us one day to protect ourselves fully from USB attacks. In their work, they presented to us a design and implementation to enforce permissions of these USB devices by encoding user expectations into USB driver loading. This method might not be perfect, but is a way forward in getting close to constraining privileges of USB devices and is a powerful tool for securing computers and permitting these valuable devices back into enterprise environments. Well, thank you for your time. I hope you enjoyed this presentation. Please let me know if you have any questions about this presentation under my Piazza post.